From the farthest reaches of the solar system to new limits of human innovation, to the limitless possibilities of our imagination. Wherever your mission takes you, we'll be there. A partner through it all. Pushing the boundaries. Doing the impossible. Always going beyond. Ball Aerospace. Let's go beyond together.
All right, welcome back. It's time for our keynote speaker. And I so want to steal the thunder of our introduction on this one, but I've been told I can't do that. Thanks to Ball for being our sponsor of this segment, Ball Aerospace. And to introduce our speaker, I'd like to welcome Mackenzie Listrip. She's a VP and General Manager for Civil Space for Ball, and she's located in Colorado. Mackenzie, please take it away.
Yeah, thank you so much, Alan. Appreciate it. I'm so pleased to be here on behalf of Ball to introduce Dr. Ellen Stofan. Many of us have had the joy of working with Ellen and knowing her over her more than 25 years as an impactful leader and a very distinguished planetary scientist. I want to congratulate her for her role, recent role as Undersecretary for Science and Research at Smithsonian. Very excited to have her there. In this role, she leads the institution's collective scientific efforts and commitment to research. Among those initiatives are very timely topics such as global health, climate change, biodiversity, species conservation, astrophysics, and the search for life. And previously, Ellen was the director of the Smithsonian's National Air and Space Museum, and she led the museum's research on planetary science, aviation, and spaceflight history. She's also previously served as NASA's chief scientist, advising on strategic planning and programs, including guiding development for the long-range plans to get humans to Mars. And her research record as a planetary scientist is very extensive. But today, her topic is going to be exploring the area of expertise in that long-range planning for humans. And her talk is entitled Moving Humans Beyond Earth. So very warm welcome to Dr. Ellen Stofan. Thank you.
Thank you, Mackenzie, for that lovely introduction. And if we could bring up my slides, that would be great. Again, thank you for having me here at the Goddard. I always love participating in this symposium, and it's obviously been an amazing lineup of speakers over the last few days. Really impressive and really fun. Next slide, please. So even after 20 years of us being on the International Space Station, for many of us, especially those of us of a certain age, moving humans beyond Earth still means talking about Apollo. And I wanted to use this opportunity just to once again mourn the loss of Michael Collins this past week. An amazingly lovely individual, truly thoughtful, such an explorer, such a great individual, and of course, near and dear to my heart as the founding director of the National Air and Space Museum. 2 years ago when it seems like an eternity now, especially all those people standing next to each other out in the National Mall. But that 50th anniversary of Apollo, to me, really reminded us of the fact of, we all know that the reason that we were successful in moving humans beyond Earth was because there was a huge geopolitical driver that moved us all forward. But I think that celebration last summer, 2 summers ago, really spoke to the fact that beyond those geopolitical reasons for exploring, beyond economic reasons for exploring, technology investment, moving technology forward, beyond the science that's so important to me is the inspiration piece. And when you consider the faces of kids that were out on the mall, and I urge you, if you haven't seen it, to watch our Go for the Moon video available on YouTube from the Air and Space Museum. The faces of kids watching the retelling of that story and seeing them get that inspiration. And obviously we know from people from Jeff Bezos to Pavya Lal, Apollo inspired an entire generation of people who not just went into NASA, to spaceflight, to technology, to all kinds of fields. So as we think about this issue of moving humans beyond Earth, all those reasons for which we do so are really critical. But to me, this inspiration piece really stands out. Next slide. Obviously, from the example of Apollo, it's clear that we learned an awful lot. I mean, scientifically, even though it wasn't the reason we went, scientifically, we got a huge return. And I know there was a panel on that earlier today talking about lunar exploration, what we've learned, but obviously what there is left to learn. But obviously concerning to all of us who care about moving humans beyond low Earth orbit, there's this question of sustainability. And clearly Apollo was not sustainable. Why were we there? Why did we go? As soon as we got it done, the rationale for continuing had gone away. It lacked relevance and the program died. And obviously, as we go through and think about moving humans beyond low Earth orbit again, one of the things we really worry about constantly is sustainability. And you hear always people talking about, we don't want flags and footprints. We want actual sustainability of moving humans beyond low Earth orbit. Next slide. Now I'm jumping here, but stay with me. You know, for a lot of us who worked at NASA or worked with NASA data, when the shuttle program ended, I had so many people come up to me and say, "Oh, I'm so sorry you lost your job." And I was like, "What are you talking about?" And it was this whole issue that people so closely identify the human spaceflight program with NASA that when the shuttle went away, they thought NASA went away. But for those of us who worked at NASA, understood that, first of all, it hadn't gone away. We had people up in the International Space Station. But beyond that, what NASA had been accomplishing since Apollo scientifically is incredible. And obviously, you've heard about that over the last several days, and you're going to hear more about it this afternoon. Because of NASA missions like Kepler, because of the exploration we've done of Mars over the last 20 years, because of our explorations of our sun, the science that has been returned over the history of NASA is actually mind-blowing. The point where we started in the 60s versus our understanding of our universe, our galaxy, our solar system is really incredible. And to me, nothing has been more incredible than the last 20 years, where we have this incredible revolution going on in finding planets around other stars, answering or getting us closer to the answer of a question that people, I think, have had basically since there have been people, of, are we alone? Is there life beyond Earth? And the fact that Kepler got us to the point where we could understand that just about every star that we see has a planetary system around it has really moved our thinking forward. Next slide. And as we look at those planets coming back, and the fact that so many of them are in this Earth to Neptune size test is obviously taking us, the Transiting Exoplanet Survey satellite is taking us to the next level, finding more of these Earth-sized planets around other stars. It's moving us forward in this idea of we're actually searching for this Earth 2.0. And with James Webb coming closer to launch, being able to look at the atmospheres of exoplanets, doing some of the ground-based work we do to look at atmospheres of exoplanets, we're getting closer and closer to finding Earth 2.0. But one of the things I really love, and this is a slide I got from Dave Grinspoon originally Don Brownlee, what Earth 2.0 are we actually going to find? And for me as a geologist, that early Earth 2.0, these are all the Earth, by the way, in different stages of its evolution. So to me, the most fascinating Earth 2.0 I actually want to find is the one up in the upper left, magma ocean Earth, but cyanobacteria Earth, snowball Earth, future Earth. We have to keep in mind that as we're searching for habitable planets around other stars, we're finding them in different stages of evolution, at which point they may be habitable of a sort, they may not be habitable at all. And this evolution is something that we've also only been able to come to understand because of the last decades of exploration. Next slide. So in our own solar system, because to calibrate this likelihood of finding life beyond Earth, it really comes back to our own solar system to really understand where are the possible targets that we could look in our own solar system for a possible second or even third genesis or beyond of life. And so we have a number of targets, Venus up there in the upper left, some intriguing atmospheric results recently that might not have amounted to anything, but still really interesting. There's people who talk about potential for life on Venus. And we certainly know that early Venus was likely very wet. That period didn't last very long. Was it long enough? And can we find traces of that by better understanding the planet, and hope to go back there soon? Obviously, the whole set of on the right side of the slide are not at all in what we had thought of as the place to search for life, the habitable zone around a star, but the moons of the icy moons of the outer solar system, whether it's Europa on top or Enceladus in the middle, where you have an icy crust and a subsurface liquid water ocean where you could be searching for life, or whether it's a more exotic location like Titan on the bottom right, where it's really an opportunity to be thinking about what are the limits of life. You don't have water, which we think is critical to life, but you have liquid hydrocarbons. And so is that a sufficient environment in which to find life? And obviously the Dragonfly mission will go the next step in sort of looking, could we find evidence of prebiotic type chemistry? But obviously, as we look at all of these targets that have the potential for life in our solar system, the one we've been most focused on is obviously in the lower left, and that's Mars. And you all know the long history of why Mars is the likely candidate. From about 3.5 to 4 billion years ago, Mars was wet. Standing water on the surface. We've learned this over the multiple missions that we've had. And so Mars had conditions very similar to those around the same time period when life evolved here on Earth. So could life have evolved on Mars? You know, based scientifically, we think it did. It had the exact same conditions. Why wouldn't it have? So when we think about this search for life, Mars becomes the logical target to go to be able to study in depth. It's not that we won't go to Venus. It's not that we won't go to Europa or Enceladus or Titan, but Mars offers us a platform to really get to the bottom of not just did life evolve, but to what complexity did it get? Next slide. And obviously right now we're in the middle of studying Jezero Crater. This is obviously for, I think everybody on this webinar probably recognizes this place. We've all come to know it over the last several months since Perseverance's landing back in February. And the fact that we are able now to ask such sophisticated questions about Mars using this combination of different types of orbital data that we've gathered, and then actually send these rovers down to the surface and even helicopters down to the surface to really start exploring and asking more and more detailed questions. Okay, we've gone from understanding Mars could have been habitable to, okay, those conditions were actually conducive to life. Next slide. As we've seen, next slide. As we've seen, and this is just one of the rock outcrops at Gale Crater that Curiosity has looked at. When you see these layers of rock that we now understand do represent time periods in the history of Mars when the potential for habitability was actually fairly high. And then you say, all right, how are we actually going to take that from saying it has the potential to finding evidence? And obviously Perseverance will take the next step on this, which with an ever increasing complexity of instruments that it has on board. but it is also, of course, going to cache a sample for hopefully future return to Earth. But that is one small sample. And if we really want to understand, again, not just did life evolve on Mars, but to what complexity did it get? How widespread was it? And of course, an ongoing question of whether there is still extant life on Mars. There is I have long argued that it is going to take humans on Mars breaking open a lot of rocks, analyzing and assessing all these different layers of rock on Mars to really get at understanding the extent to which life could have evolved on the planet. Next slide. But you all know this, the human exploration of Mars is going to be difficult. So this issue of how do we get from where we are now in low Earth orbit to having a sustainable presence of humans out in the solar system, there are certain things we've got to overcome. Certainly the ability to land very large payloads on Mars is one of the chief impediments I see that we're still pretty far from. As big as Curiosity and Perseverance are, we all know they're nowhere near the amount. Those technologies that we use are going to have to really change. We're going to have to do a lot of work and investment in order to get entry, descent, and landing systems for the amount of stuff that humans will need and human systems. We also know that on the way to Mars, you're going to be subjected to a lot of radiation. There's ways to protect humans. We're working on that, but still a big problem. Long two-way communication once you get there. We need faster propulsion, and we certainly need reliable power on the surface. So a lot of logistics problems. One thing I would point out, though, is all of the challenges that we faced when Kennedy gave his Rice speech in 1961 were way harder than a lot of the things on this slide. And yet 8.5 years later, we landed humans on the surface of the moon. So I think it's really important to always keep these things in perspective. Yes, getting to Mars is hard. Yes, human exploration of Mars is hard. But human exploration of the moon was even harder because there was so much that we actually didn't know. We actually have a fairly good understanding at this point of what it is we need to do. And I should have called out ISRU is on there. Obviously excited that the first working of MOXIE on the surface was successful on Perseverance. Next slide. Now, and the other good part now, again, an advantage that we did not have on Apollo, we've been spending the last 20 years learning how to live in space long duration. Huge success of the International Space Station in terms of really understanding how to keep humans healthy for long durations in space, how to develop technologies, how to develop eclipse systems. The depth and breadth of the preparation work that we have done over the last 20 years on the ISS, in my mind, cannot be underemphasized or under-celebrated because it is a huge achievement of the international partnership in terms of really getting humans ready to move beyond low Earth orbit. Next slide. The other thing that we're obviously still struggling with is how do you get affordable architectures to get humans to Mars? This is a vintage architecture that I brought out. It was just Nadiri et al., the Fruz and the group at JPL put together in 2015, trying to look at, and this is just one of, we all know, many, many architectures that have been looked at over the years. Really trying to look at what would be a minimal architecture to get to Mars. And obviously you have to say, you know, what tools do you have? For example, this architecture relied totally on the SLS. How long are you going to stay? How many people are you going to stand? Are you going to land on the first mission? Are you just going to orbit on the first mission? So there's lots of optionality when you look at architectures. But to me, one of the most important things is it a sustainable architecture? Back to this question of, again, always haunting us in the back of our mind is why didn't we stay for longer periods of time? on the moon. We all know there's a lot of history there, a lot of work that's been done to explain that, but how do we avoid that going forward? And so do we have a flexible architecture? Do we have an affordable architecture? These are questions that I think as we move forward, moving humans out to the moon and then onto Mars, we really need to keep pushing on this building sustainable, flexible architectures as we go forward. Next slide. And obviously, as we work to develop things like Gateway that are underway, I think we really need, and the human landing system that's being developed for landing on the surface of the moon, we really, in my mind, need to be constantly pushing on, are we designing for Mars sustainability? We're testing technologies at the moon to get ready to send humans to Mars. So are we keeping Mars in the back of our mind? Are we pushing the technologies in that direction? And are we really optimizing to do what we need to do to be ready as soon as possible? And I think that should be at least partially what is driving the design of things like Gateway and the design of systems as we move forward. Next slide. I love this slide. It's actually, that arrow is obviously pointing out a little star in the sky that is Earth. From the surface of Mars. And hopefully we are all going to live to see a human one day, knowing that a human is seeing this view from the surface of Mars. But I think it's really critical, again, to always get back to that word sustainably. How do we develop, push technologies where we need to push them, whether here at Earth, whether on the moon, whether in lunar orbit, to get ready to get to Mars, but make sure we're really optimizing how and where we test technologies to do this in as an affordable way as we possibly can, and to build flexibility in things like multiple launch vehicles, for example. Next slide. You know, yesterday, obviously, a lot of the talks, including the keynote by Gavin Schmidt, focused on sustainability of a different kind. And I think also as we think about the importance of moving humans beyond Earth, we cannot underestimate the importance of making sure that this planet, which is the only planet that we can actually live sustainably on, that we are doing everything we can to understand this planet. And the fact that we do understand that climate change is happening and can understand the effects of it and understand how to become more resilient to the effects of climate change is due to this long history of NASA Earth observations. Really critical and really important. Next slide. And I never like to give a talk without somehow managing to talk about SERVIR, which is a NASA USAID program where we work with where NASA works with countries around the world to use Earth observation data to help make them more resilient to the changes that are happening, whether it's more severe weather, whether it's water shortages, too much water, microalgae blooms. These are the things that we can use Earth observation data to help not just make our country safer, but to help gain stability around the world by teaching other countries how to use that data to improve their countries. Next slide. And the work that we do at the Smithsonian is very aligned with this. As Mackenzie was saying in the beginning, at the Smithsonian, we're doing that really critical work where you have to combine the Earth observation data with data on the ground to really understand, calibrate what's happening, and be able to come up with solutions. So whether it's the forest work we do about trying to understand how to restore forests, protect the biodiversity within them, using data to understand how the migration of animals, the effects of reintroduction, whether it's really looking at how to make coastlines more resilient and things like blue carbon storage in seagrasses. This research that's done, whether by NASA or in other areas, this combination of research is so critical right now in terms of making us more and more resilient to the effects of climate change. But obviously, as the Smithsonian, one of our big jobs is to also try to explain all of this to the public. And so whether it's exhibits like the one on the top right of Deep Time, where we talk about climate change, and put it in the context of this longer history of the Earth to help people understand that the climate has changed and what the effects of anthropogenic climate change are going to be and could be if it gets worse, are really critical. And whether it's addressing issues like environmental justice through the work that we do with the Anacostia Community Museum here in Washington, D.C., protecting local rivers. These kind of work are critically important. Next slide. And I just wanted to end on the fact that whether it's moving humans beyond Earth or understanding that the Earth needs how critical space observation data is to protecting this Earth in combination with the data we collect on the ground, it's also critically important to all of us, I know, that we certainly understand and honor people like the Apollo 11 crew, as I mentioned, Mike, at the beginning of this talk. But I think it's equally important that those three people at the bottom are just as well known as the Wright brothers or Chuck Yeager. Because if we really want to move forward and tackle these really tough problems, it's essential that we diversify our workforce. And that means creating more inclusive workforces. It's making sure that every kid knows who Bessie Coleman is or Charlie Bolden is. It's making sure that we really value the contributions of everybody and inspire every kid to become part of this great enterprise of space exploration that we all love so much. So thank you for having me here today. And I think we have time for a couple questions.
Thank you, Ellen. We appreciate it. And we do have time for a couple of questions. The first one came in early, but it related to something you said at the end when you started talking about your role at the Smithsonian and helping folks understand things in context. So how has the populace changed in their attitude towards science over the past few years and towards science driving things? And not talking about COVID, leave COVID out of the discussion, but the large science things that you were talking about, how has the public attitude toward those things changed since you left NASA?
You know, I think one of the really positive things I've seen is, and this is out of some Pew Research data that my colleague Catherine Hayhoe likes to show. So if you look now, about 70 to 75% of Americans actually accept that climate change is happening. That's really critical, right? Because we've got a lot of hard decisions to make about how to start decarbonizing our economy and resilience to climate change effects. So that 72% or so that now accept climate change, that's critically important. What's really interesting though, is if you ask them a different question, is climate change going to affect you? The answer drops down to about 40%, except right along the coast. Everybody on the coast is like, yeah, that sea level rise thing's gonna affect me. So I think in some areas we see public acceptance of science growing, but I'm still really concerned that people don't understand the scientific method. They don't, because when you see things like reaction to vaccines or some of the reactions that we have seen in the past to issues around climate, that it's really important that people understand kind of evidence-based thinking. And it's really important as a science and engineering community to make sure that when we talk to the public, we just don't shout louder and louder at them what the facts are, because we see that doesn't actually work. But we really work with the social science community to think about how do we get scientific concepts across. And I think there is public support for the space program, but it's probably not as high as we would all like it to be. And I think that's on us partially to think about, how do we talk to the public about space exploration? How do we talk about what we do in a way that's impactful? We've got to reach beyond what I call the nerd public, which are people who already love us, and broaden that out.
Okay, I have a time for a 30-second answer, so I'm going to ask a trite question. Did The Martian help or hurt?
I think it helped. Of course I'm biased, but I think it really helped. I think it excited people. People want something to dream about. They want something positive. The Martian gave us that. Space exploration, that's why we had 1 million people out on the National Mall to watch a rocket projected on the Washington Monument.
I would love to have seen that. All right, folks, this is the end of this session. Ellen, thank you very much. I appreciate the time I hear you talk.
Thank you.
And now it's time for us to go off to our next session, which is exoplanets and unifying space sciences. So if you go to the top of your screen and click on go to the next session, you'll go into it automatically. Jim Wei is waiting for you there. Thank you, Mackenzie and Ellen, and thank you for our staff moving us forward.